Salam. Hello, good morning, good afternoon, good evening. Welcome to this webinar. My name is Yasser Hassesaz from Nuclear Science and Technology Research Institute of Iran. And I am so happy to be here as the moderator of this webinar. Today's webinar is related to nuclear fuel cycle. You know that there are several nuclear power plants in the world. Currently, there are more than 450 nuclear power plants around the world that they are totally generate 10 to 11% of total generated electricity in the world. All of them needs nuclear fuel. So today we will learn, we see how this nuclear fuel is produced and what are the main procedures, what are the main actions to produce nuclear fuel. Also, we will learn what happens to spent nuclear fuel after using in a nuclear power plant. Let me introduce, it is my pleasure to introduce our speakers today, Dr. Qannadi. Professor Qannadi is a full professor in Nuclear Science and Technology Research Institute of Iran. He has done several outstanding work in different field of nuclear technology in the country. Professor Qannadi, thank you so much for joining us today, and the floor is yours. Thank you.
In the name of God, the compassionate, the merciful, on behalf of the Atomic Energy Organization of Iran, I would like to express my sincere thanks to organizer of ANET in everywhere of the world. I would like to also express my thanks to Yasser, my dear colleague here as a moderator. I am pleased to be with you for a while, an hour or so, to talk about nuclear fuel cycle as a general. Actually, one day my teacher told me a few words. I want to tell you these things. He was saying that if you want to learn something, you read about it. If you want to realize something, you write about it. If you want to be dominant about something, you should share with others. So I would like to share my word with you, and I will have my speak here about nuclear fuel cycle from mine to waste management. Well, without nuclear fuel cycle, there will be no nuclear industry. From point of providing electricity in nuclear power plants, research reactors to provide radioisotopes for medicine, agriculture, and industry. Well, maybe you know many things about uranium, but I want to tell you a few words, very important. You know, in nature, there are some elements which are vital for human beings, for health, for industry, for agriculture. For example, oxygen, hydrogen, iron, and iodine, potassium, sodium, and other elements which are vital for human beings. Without them, there is no human being, there will be no health, there will be no industry, and many things. Among of these, only one element is very, very important, and it is uranium. Why it is important? Because uranium is a natural element which has been created from the beginning of the world. And this element has a very long half-life that existed now too. But the point is this one, uranium has no application, any application in industry and other things. Uranium has only one application, and this application is in nuclear, which means that if there is no nuclear industry, there is no use of uranium. Uranium itself exists in mines in everywhere in the world, in granite, in phosphate, and seawater, with different concentrations. But the point is this one, if we want to use uranium, we should do some works. And these works are fuel cycle, starting from mining. Uranium itself is an element, and it is radioactive. It exists in 3 isotopes. The main isotope is uranium-238, 99.3%, 0.7% uranium-235, and remaining very small amount, uranium-234. Uranium-234 is the daughter of uranium-238. Has no use. The main application of uranium-35 and uranium-238. This means that uranium-238 in reactors has no application for fission, but uranium-235 is something else. It is fissionable, and its half-life is a little bit less than uranium-238. If you can see this picture, it's very nice, explaining how uranium-238 goes for decay and disintegration, and at the end, it stops in lead. Uranium-235 also is like that, but it is the main one. That's why we have brought it here. It radiates alpha particles. Well, this picture is very nice and explaining how uranium-235 is fissionable. You know, the cross-section for uranium-235, cross-section means that if a neutron, thermal neutron, enters to uranium-235 nucleus, it will be highly excited and it splits into other elements and radioisotopes. From one atom to another radioisotopes are produced, and also 2 to 3 neutrons are produced, and also very, very big amount of energy. It means 200 million electron volt energy from one atom. I want to tell you something very interesting here. If a neutron collide to uranium-235, it will give you maybe, we can say 2 neutrons is produced again. Those neutrons go again for fission of uranium-235, the remaining one, and it goes further and further. So the chain reaction of fission happens here. I will tell you something very interesting, that if, for example, if it collides 100 times, we will have 2 to the power of 100 neutrons produced and fissions. So many, 2 to the power 100 means 10 to the power 30 neutrons are produced here. And it is very, very astonishing. Nothing happens in nature like that, and nothing happens in industry like that, like this one. Only uranium-235 is like this. But uranium-238 is not fissionable. It captures neutron. After that, after some processes, it will give us plutonium-239. So from this energy, which one atom of uranium gives 200 million electron volt, we can have this very big amount of energy from many atoms of uranium. So it will give us very big energy. We can use this energy in nuclear industry and in producing of electricity. Well, what you can see here, very small plate of uranium, which I'll explain how it comes from there. Only one plate of uranium, which is extracted from mining, and also it comes as a UO2. It will be about 7 grams of weight and about 1 centimeter of tall and half a centimeter diameter. One small plate gives you 1 ton coal energy if it splits. And natural uranium produces energy in heavy water reactors. Heavy water means that only heavy water used because it is natural uranium. There is no need for enrichment. I will explain it to you. But whole light water reactors, pressurized water reactor, boiling water reactor, use uranium enriched one. This enrichment should be about 3 to 5, average about 4% of it. Altogether, in 1,025, 63,000 of your natural uranium has been used in 416 nuclear power plants in 31 countries. You can see here nuclear power plants as a whole. There are some power plants. Their name is boiling water reactor, which use about 3-4% enriched uranium, moderator and coolant of water. Pressure water reactor enriched in uranium dioxide, enriched again about 3-4%. And water also again is coolant and moderator. Pressure water heavy reactor is CANDU. CANDU means that Canadian deuterium uranium reactors, which natural uranium is used there. In here, heavy water D2O, because deuterium has cross section very low, so it should very low. Short neutrons is not wasted, and it can be used again for splitting of uranium. That's why we can use, if we want these reactors, and also again advanced gas reactors were first reactors in United Kingdom, which they are very old at the moment. Carbon dioxide was coolant and graphite was moderator. Another reactor is water cooled and graphite moderator, RBMK in Russia, which enriched uranium 3-4%, and water is coolant and like that. And fast breeder reactor you see, which is uranium and plutonium. I will explain a little bit about that. Well, one thing I want to tell you here, this is nuclear fuel cycle for light water reactors. Light water reactors mean pressurized water reactor or boiling water reactors. Somebody was telling me that a chain, if you have a chain, the strength of chain is in the weakest ring of it. It means that all the rings should be safe to have a good chain. This chain, if nuclear fuel cycle, should have from mining to waste so many rings inside it, so many processing was inside it. But all of them should be very sophisticated and very industrialized industry, very high sophisticated industries there. You can see here from mining of uranium, and it goes to yellow cake. I want to tell you something here. Between yellow cake, which ordinarily is in selling and buying in the world, U3O8 itself is not yellow cake. Yellow cake is ammonium oranyl carbonate, I'll tell you, and ammonium dioranate. This ammonium oranyl carbonate and ammonium dioranate reduced to U3O8. U3O8 is not itself existed. It is existed as UO2 and 2UO3. UO3 in orange color and UO2 is black color. When you mix two to each other, it will be olive color, which is U3O8 and is in the stock market in the world as a crude oil. You can buy and sell it in the world like that. After yellow cake, it will be a conversion facilities. It means that U3O8 should be converted to UF6, which I will tell you later on. UF6 goes into enrichment. In enrichment, you will have enriched uranium and depleted uranium. You can see here. This is depleted uranium here, and this is enrichment facilities, and this is enriched uranium. It goes for fuel fabrication here. Yeah? And after fuel fabrication, it will be in fuel assemblies. After fuel assemblies, it will be to the reactor. After reactor, spent fuel comes here. You see, I will tell you a little bit about spent fuels later on, but here is spent fuel. Spent fuel here, after using of the uranium in the reactor, after that, it will be spent fuel storage, like this, you can see here. After that, if you had anything, reprocessing, I mean, separation of uranium, plutonium, and fission products, see here. After that, uranium can go again to reactors and plutonium to fast reactors. And this is waste management here, you can see here. It's very complicated, very sophisticated, very highly scaled engineering. What different is here for CANDU reactors? CANDU reactors, they are known for enrichment. They need only heavy water for cooling and moderating. You can see here, mining and milling, refining, and pressing like this here. The relatively different fuel cycle in this. You can see the mass balance here from ore to actually to the reactor. For example, if you want to use it as a reactor, starting from there, uranium fuel. See, this is very nice mass balance here, starting from ore, mining and milling, natural uranium conversion like this, and comes here UF6, UO2, and UO2 comes to fabrication, reactor, and spent fuel storage. You see, if you want to have a 1,000 megawatt electric here, which means 7,445 gigawatt hour electricity, it comes from here. You must use this amount of uranium from ore to reach 30 tons of UO2 as 3 to 4% enriched. Well, uranium fuel resources in the world are very different, you see. If you have very good mines, deposits, it will be about 20% uranium. I saw something in a book. There is a place, there is a site in Canada. It is called Saskatchewan. It has 70% of uranium. It is very high level deposit there, you see. And anyway, 20% is very high level, very high grade mineral. After that, 2% or 0.5%. Coming down, you can see here granites, sedimentary rocks, and also seawater. Uranium exists in all of the world with different amount. For example, seawater has about 3 ppb part per billion uranium in water. So much uranium existing in seawater, oceans, and rivers. How it goes to exploration of uranium. See, if it's starting from the satellites, from airplane, from helicopters, from mining like that, boreholing and getting some sample from there and examining them for to have uranium. Uranium is not existed as uranium metal in the deposits. And it is accompanied with other elements such as molybdenum, iron, copper, gold. For example, in South Africa, I was reading in a book, uh, it is gold mining and as a product. Uranium is byproduct of the gold in that country. So many countries have uranium accompanied by many elements. It depends on the deposit there. So you can see in this picture how uranium is uh, deposited in all over the world. It is very astonishing. You see, except Niger, here is about 7% of uranium of the world are there. Others on the north and south of the planet. See, north and south of the globe. I don't know what is the reason. Maybe the reason is this one because density of uranium is very high, about 90 gram per cubic centimeter. When globe was running, when the Earth was rotating very fast in the beginning of its creation, maybe
Dr. Yasser, do you hear me?
can you hear me, please?
Yes, I can hear.
Okay, 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 okay. So you can see how to explore uranium, and it is mining the actually you can see how is the mining here. You can get uranium from depths of the earth. Well, this is very nice here. You can see yellow cake here. As I told you, to see ammonium uranyl carbonate and also ammonium diuranite. When it is reduced, it will be U3O8 like this. As I told you, U3O8 is a mixture of UO2 and UO3. UO3 is uh, orange color and UO2 is black. So altogether, it will be olive color like this here. This is the last point of producing yellow cake. And this is uh, how to extract uranium from mine. two kinds of leaching is here, acid leaching and alkaline leaching, was very actually difficult procedures. You can use these kind of works to get uranium as uranium U3O8. This is, you can see here, very complicated, very highly engineered processor here, uranium deposit from here. This is radiometric sorting. It means that separating of uranium with a high grade and low grade. At that case, you can separate with each other. And here, cone crusher and crushing of all elements here. And these are processes, wet milling, thickener tank, which means to concentrate it, and acid leaching, uranium adsorption in resin. Resin is some chemical elements. You can separate many elements from uranium there, and uranium recovery. Coming to solvent extraction means extraction by some extractors like tributyl phosphate or ammonium, all these things. And after that, you will have here AUC or AU3C and or ADU. And after that, filtration as the last point here in yellow cake production is this one here. You can use it in barrel like this here. You can see as U3O8, which after that, it will go to, in fact, for conversion. This is yellow cake or U3O8. After that, uranium in solution, ATC or AUC, UO3 here, which reduction, after reduction will be UO2 here. In conversion, you will have UF4, first UF4, after that UF6, you can see here, and as a sample like this. Very complicated, very hard working for industrial methods for UF6 production. It is very sophisticated, very difficult, some process of engineering. It is like chemical engineering work, mechanical engineering work. All engineers are shared in this work. Very difficult situation here. It takes a long time. Two methods are here, wet method and dry method. I'm not going to explain all these works, but the last production is pure UF6. Here you have the main compound of this. Well, here I will tell you one thing very interesting. Actually, UO2, if you go to UF6, it will go via UF4. First, UF4 is produced. After that, by fluorine, you will have UF6 here. But there is something very nice here to have a notice here. You see, uranium hexafluoride, UF6, has triple point work. It means that at 60 degrees Celsius, it is gas, solid, and liquid. Nothing is like this in any element. Only UF6 is like this. It's very important, this one. That's why when UF6 is produced, you bring it, compress it, and you bring the temperature down. It will be as liquid or solid. After that, you can send it for enrichment to enrichment facilities. Here you can see enrichment here. It means that UF6 comes from heat and enrichment facilities. And after that, you see UF6 as enriched, maybe 2-3% for nuclear power plants and 20% for research reactors. For example, research reactors use 20% uranium, 20% enriched uranium as a plate. You can use, for example, our research reactor in Tehran is has used 20% of uranium. All over the world is like this. There are so many ways and routes for actually enrichment. One of them is gas diffusion. This gas diffusion is used only in France and UF6, natural UF6 goes from here and goes here again, but compressed and with temperature, and goes out and enriched steam and depleted uranium like here. The only point in diffusion is using a very high amount of electricity. For example, for diffusion in France, you will have four PWR reactors. It is about 4,000 megawatt electric to do diffusion. This is the main reason it is very difficult situation. That's why centrifuge, like here, it can use for you. There is no use of electricity that much, but very high level and very sophisticated equipment here. See, in rotating 60,000 rotation in 1 minute goes here, and UFCs come, natural UFCs come from here, is feeding, and light and heavy fraction come right here. I mean, depleted one from here, and enriched one comes from there. Actually, many countries like Germany and Holland and United Kingdom as Urenco, or in United States or Soviet Union and some other countries have this kind of enrichment facilities for themselves. Another route for enrichment is by laser. It's very sophisticated and very, very expensive. Not many countries do like this. Is in the stage of research and development. I think it's not industrial yet, but it is very sophisticated work there. Nuclear fuel is like this. You see, if you want to use it in a nuclear power plant, uh, powder of UO2 should be pressed first. At that time, the lubricant is used with it. And also, its density at that time will be about 6 grams per cubic centimeter. After that, it should be sintered. That means that about 1,700 degrees centigrade heat should be there. At that time, lubricant goes out, and also it will be density about 11 grams per cubic centimeter. The reason for this is two reasons for that. One reason is this one: the lubricant will go out because it's there. Oil, it's an oil, and after that, it should be as a ceramic one and very compressed and very concentrated, so you can use it in the reactors like this. So we are coming to fuel rod. It is like this. These are fuel plates like this, and it goes to PWR reactors, VVR reactors, boiling water reactors, CANDU reactors, and this is assembly of reactor fuel. So this is another shape from UF6 to UO2, and goes to fuel assemblies to the reactor. And this is very simple shape for that. But after UF6 is enriched, it should be converted to UO2 again to go as a plate. That's why we come here, for example, UF6 enriched one as a gas goes as a steam to be UO2 F2. After that, it will reduce to UO2 powder. Two routes are here: wet method and dry method like this. Both of them are very good and very important. Any country for itself do like this for that. And this is fuel production, pellet production, very, very sophisticated, very expensive, and it needs very good quality control. That's why it is. There is a question here: why we don't use it as a powder uranium oxide? It is two reasons for that. First one is this one: it should be compressed because neutron, when neutron neutron comes to the nuclear ceramic pellet, it cannot go out. It will split uranium-235. This is the first reason. And second one, it will be concentrated and condensed. So very low volume it needs to be fabricated in the fuel assemblies. That's why this route is from powder storage like this, and it goes from sintering about 1,700 degree Celsius needs for this one. And this is again a factory of fuel fabrication, very sophisticated, very complicated process of engineering, mechanical engineering, metallurgical engineering, chemical engineering, and quality control is needed for this one. And many fuel assemblies are inside, very fuel elements are inside fuel assembly. After that, go to the reactor. So when uranium is inside the reactor, the difference between nuclear power plant and ordinary power plant is this one. In power plants, ordinary power plants, graphite or gas or oil is burnt as CO2 and water and ash. And it's very large amount of carbon dioxide comes out 7 million tons per year from one PWR 1000 megawatt. And it goes off, nothing is remaining. In nuclear power plant, it's completely different. From 100% of nuclear fuel, 95% is remaining as uranium-235, but enriched in 1%. Plutonium is produced and another transuranium elements, and also fission products. So it doesn't finish. It is not, for example, just like power plant. For example, if you want to have it, it should be only spent fuel. So you have uranium, you have plutonium and transuranium elements, and also fission products which are produced there. Firstly, you keep them in pooling here, in pools like this for a while, for 2 to 3 years. After that, or something like that, the activity decays like this. And you see, one thing I will tell you, it's very important. One fuel assembly, which has 120 fuel rods, when it goes out of the reactor, it has 10 to the power 9 curies activity. Very, very, very high activity. It's not very easy to handle it. It should be kept in water to be cooled like this. After that, you can use it just like this, these canisters. You put them there and you keep it. After that, the main process, again, highly sophisticated, very expensive process is reprocessing. Reprocessing means that you must separate uranium, plutonium, and fission products. Uranium to be used again to nuclear power plants, enriched again from 1% to 3-4%. Plutonium is used as fuel in fast-breeder reactors, and some transuranium elements, for example, americium, curium, are separated for industrial use. Cesium, strontium are separated again for in medicine and also industry. After that, some fission products to be kept for a long time, which is, you can see here. You see, these routes are very, very sophisticated, very hard and very expensive. Two steps are very important in nuclear fuel cycle, as like others, but two things. One of them is enrichment, another one reprocessing. These two routes are very expensive, very sophisticated, very excited work here. So disposal of spent fuel like this here. You can see canisters, fuel elements there. You can keep it on the ground for a long time. Some countries like Sweden, United States, and Germany, they are keeping these canisters for a long time underground. But some countries reprocess them. You can see how to keep them in underground. Just you can see again here, preparation and conditioning, and these are spent fuel. There are four spent fuel actually. Very low level waste, very low and low level waste, medium level waste, and high level waste. Low level waste and medium level waste are kept like this. It's not very difficult to keep them, but high level waste, there's a bit another work should be done there. For high level waste, you should use vitrification. Vitrification means that you should extract these fission products and put them in cement or make it glass like this you can see here. This is vitrification method to be glass. I want to tell you something very interesting. You see, if somebody with 70 years old use nuclear electricity for whole life, everything from nuclear electricity, the waste coming from there will be this size, this one. This is only for one man for 70 years. So you can imagine how important was nuclear fuel cycle, how it's very sophisticated. Thank you so much for your attention. I would like to thank you very much. If there is any question, if I am able, I will answer your questions. Thank you so much again for the coordinators of ANET, and I am here with you for a while.
Okay, thank you, Professor Kannadi, for that wonderful presentations. Now we will have move on the Q&A session. If dear participant, if you have any questions, you can use chat box. Also, if you need, you can raise your hand. I will read your question to Dr. Kannadi. Please. Is there any comments or questions? Okay, I see by Negar Mofhan. Mofhan, yeah. Pierre Moro, can you turn on his microphone?
Hi to everyone.
Hi.
Did you have my voice?
Yes,
Hi.
it is.
Okay. Hi to everyone and everyone that participate in this online webinar. I'm very glad and very pleased that the Professor Kannadi, you are my fellow citizen in the city of Maraghe, and I'm very glad to participate in this online webinar. I have just one question. My specialist um, uh, uh, is about the international human rights and international public law. But I haven't very sophisticated in this regard, in these subjects like this. But I have one question in this area about the yellow cake, Professor. You said that yellow cake is a crude and transportable concentrate of uranium oxide U3O8. Is it right? Also you said that it's an intermediate product awaiting conversion to UF6 for enrichment or to metal for specialized uses. What is the different compound of some elements in the uranium carbide. I want to know more about the uranium carbide that is a different compound of uranium plus carbon. Please explain in this regard more. Thanks for your response. Thanks a lot.
Actually, as I told you, uranium, which is converted to uranium uranyl carbonate or ammonium or uranium diuranate. This intermediate compound, you see, when it goes to rotary kiln, which is a producing of U3O8 at that time. U3O8 is not itself yellow cake because its color is not yellow at all. AUC and ADU only are yellow colors. But when it goes to be U3O8, U3O8 again is in two kinds, UO2 and UO3. I think you asked about uranyl carbonate. Uranyl carbonate, uranyl carbonate, it is not uranyl carbonate only. It's ammonium uranyl carbonate. It's a very a compound very as a cake and yellow color. Sometimes it is ammonium diuranate. It goes to U3O8 in the intermediate route. After that, you go to UF6. I am a little bit astonished that your question was about ammonium uranyl carbonate or ammonium diuranate. So, sometimes uranyl carbonate is used as a fuel in some reactors, but mainly all the reactors as PWR and BWR uses only UO2 as a fuel. But some reactors use uranyl carbide. You say uranyl carbide, yes. So I didn't understand what are your question exactly about this point.
Hi again, Professor. Thanks for your response. My question is about the yellow cake. Is yellow cake that is, for example, combined of some elements?
Can you hear me?
Yeah. I hear you. Yeah. My question is about the yellow cake elements, Professor.
Okay.
Okay, thank you, Dr. Gandhi and Ms. Mofakham for questions. Is there any comment or questions from participant? Okay, thank you so much. Thank you again, Professor Ghanadi, and also participants to joining this ANENT webinar. I'm not sure that is there Shaojing is here or not? Maru, can you check? If she has any announcement for the next webinar, we can pass the floor to Shaojing.
Let me see. I don't see her in the list of attendees here.
Okay. So thank you again, Dr. Ghanadi and dear participants for joining us today ANET webinar. I think in November we have another webinar from ANET, and I hope to see you again at that webinar. And also
Sorry,
I
I
would
have a
like to,
question. Mhm.
please.
How we can have the this live video
Yes,
record?
yes, I explain. Yes, thank you for nice
Thanks.
question. The all recorded videos for the ANET webinar will be published in the ANET website. You can go to the anetweb.org, and you can see also there are YouTube channel. You can see the recorded videos of the ANET webinar at the YouTube channel. Okay, thank you, Maru. Thank you, agency, to manage to organize this valuable this ANET webinar series. Dear Maru, the floor is yours. Thank you.
Uh, Thank you very much for thank you very much, Dr. Yasser, for moderating this wonderful webinar. As Dr. Yasser, on behalf of the Ireland as a communication officer, elaborated, the Ireland will moderate 21st webinar series in November, around 20th. So, which also looking forward to collaborating with Insta and the INSO, which are the siblings under the last our the IAEA Technical Cooperation project, centering on the educational project. So we also look forward to seeing you again, and thank you very much for paying your attention. And thank you very much, Dr. Yassel and the Professor Gani. And is it the right pronunciation, Dr. Yassel? Because it is very difficult for me to pronounce it. I'm so sorry. Professor Dr. Yassel, thank you very much again, and I'm looking forward to seeing you in the future.
Thank you. Thank you. Thank you, and bye all.